Hello, everyone. Welcome to DevFest Lafia. My name is Mustafa Adekunle, and I am a Google developer expert in Google Cloud. Today, I am thrilled to talk to you about what I believe is the next frontier in AI agents. We would explore how they are pushing the boundaries of what's possible with large language models. Here is a quick roadmap of what we will cover. We'll start with the fundamentals, defining what an AI agent is and its key characteristics. Then we will dive into the practical side with agent design pattern and communication protocol. Finally, we'll bring it all together with an application called InstaVibe to see this concept in action. So what exactly is an AI agent? In simple terms, an agent is a service that interacts with an AI model to achieve a specific goal. It uses tools and context to perform operations. You can think of it as a sophisticated layer on top of the large language models that can take action. The concept of AI agents has pretty much evolved significantly with the advancement in large language models. We started with simple LLM prompts. Then came the integration of retrieval augmented generation, which we call RAG, to pull in external data. Now we have agents that can use a multitude of tools and even collaborate in multi-agent system. This evolution represents a shift from passive text generation to active goal-oriented system. Now that we have a high-level understanding of what AI agent is, let's break down the key characteristics that define them. These characteristics form a cyclical process that enable an agent to go from understanding a request to delivering a solution. We will look at 4 distinct phases: the think, plan, act, and reflect. The first step in our agent process is to think. This is the reasoning phase. The agent takes the user prompt along with any other data it has access to and its own system instruction. It then analyzes them all together. The primary objective here is to clearly define the end goal, which is what is the user actually trying to achieve. It is also about transforming a human request into a machine understandable objective. Once the agent has a clear goal, the next step is to plan. This is the strategic phase. The agent checks through the tools it has at its disposal, things like APIs, functions, or other agents. Based on the goal defined in the think phase, it then formulates a step-by-step strategy to get there. This plan is what we call the blueprint for action. With a goal and a plan, the agent is ready to act. This is what we call the execution phase. The agent begins working through the steps defined in its plan. This can involve a wide range of actions, such as performing a RAG search to gather information, making API calls to external services, executing a piece of code, invoking other specialized agents to handle a subtask, or even pausing and requesting a human help if it encounters a situation it can't handle on its own. Finally, and perhaps the most important, the agent must reflect. This is what makes an agent truly intelligent and not just a simple automation. After the agent has acted, the agent evaluates the output of its action. Was the goal achieved successfully? Were there any errors? So based on this evaluation, it can look back over the process refining its plan to fix errors or even suggest improvements to its initial approach. This continuous feedback loop of self-critique and improvement is a cornerstone of advanced agent design. The diagram on the screen provides a more detailed look at the architecture of an AI agent. Let's break down the key components. On the right side, you see the three pillars. First, the models, which serves as the core reasoning engine. An agent isn't limited to a single model. It can use multiple specialized models to determine the plan and generate a response. Next, we have tools. These are the mechanisms the agent uses to interact with the outside world. This could be anything from functions and APIs to database. They allow the agent to fetch data and perform actions. Finally, orchestration. This is the component that brings it all together. It takes the plan derived from the LLM and executes the necessary steps, which involve invoking the right tools and maintaining the agent state or memory throughout the task. A critical design decision when building an agent is determining how it will create its plan. We can categorize this into three approaches. The first one, autonomous. This is where the agent has the highest degree of freedom. It analyzes the goal and decides on the steps all by itself. The second is prompt-driven. In this model, the plan is explicitly described and given to the agent within the prompt. In this particular part, we are essentially telling it both what to do and how to do it. And the third part, we have external workflow. Here, an external program or a predefined workflow orchestrates the process and drives the LLM, telling it what to do at each step. Each of these approaches has distinct trade-off, which we are going to explore next. Let's look at the trade-off, starting with the challenge of granting full autonomy. When an agent is autonomous or prompt-driven, we are relying heavily on the LLM's reasoning to create a correct plan. This can sometimes lead to issues like function call hallucination, where the model tries to use a tool that doesn't exist, or it might execute steps in wrong order. This can make the agent's behavior unpredictable. In contrast, an external workflow provides a much more controlled environment. Because the plan is defined in an external code, the agent behavior becomes deterministic, explicit, and predictable. This makes the system far easier to maintain and debug, as the logic is clearly laid out. On the other hand, let's consider the benefits. While an external workflow provides predictability, it can be rigid. An example of this is that any change or evolution in the plan requires a code update and maintenance. This is where the autonomous approach truly shines. It gives the agent more autonomy and a higher sense of agency, allowing the agent to adapt its plan on the fly. This makes it incredibly well suited for dynamic or constantly changing environments, where a strict, predefined plan would become obsolete. Now that we have covered the foundational concepts of what agents are and how they plan, Let's shift our focus to how we actually build them. Just like in traditional software development, there are established design patterns that provide reusable solutions to common problems. These patterns helps us create agents that are more robust, scalable, and predictable. In the next few slides, we would explore some of the important ones. Let's start with one of the most fundamental and powerful design patterns, function calling. This is the primary mechanism that allows an LLM, which is fundamentally a text processing engine, to interact with the outside world and perform real actions. Let's walk through this diagram. A user asks a question that the LLM can't answer on its own, like, what is the weather like in Lafia? Our application sends this prompt to the Gemini model, but it also sends a description of the tools it has available. In this case, a function called getWeather. Gemini intelligently determines that to answer the question, it needs to use this tool. It then generates a structured response telling the application, call the getWeather function with this specific parameter. Our application then executes that function, which might involve calling an external weather API. The API returns some data which our application then sends back to the Gemini model. Finally, with this new real-time information, Gemini formulates a natural, human-readable answer for the user. So this pattern that we explained above is what transforms an LLM from a simple chatbot into a true agent that can fetch data and get things done. Beyond simple function calling, we need ways to manage how multi-agent or model calls interact with each other. This is where control flows come in. These are patterns for orchestrating more complex workflow. If you take a look at the diagram, on the left, we have the sequential model. You can think of this like an assembly line. An input is passed from one specialized agent to the next, with each one performing a specific task in a predefined order. In the middle, we have the parallel model. This is more like a brainstorming session. The same input is sent to multiple agents concurrently, and their outputs are then aggregated to form a final response. This is great for tasks where you want to gather multiple perspectives or results at once. On the right, we have what we call the hierarchical routing. This pattern uses a router model that acts as a smart dispatcher. It analyzes the initial agent and directs it to the most appropriate specialized agent based on the user content or intents. The diagram at the bottom illustrates more dynamic flows, like a loop agent. This can repeatedly try to solve a problem until a certain condition is met, which is crucial for self-correction. And we also have the conditional LLM agent that can make decisions and change its path based on intermediate results. As we give agents more autonomy, we also have to consider the implication. Not all agents or not all decisions should be fully automated. This brings us to a crucial design pattern for building responsible and safe AI systems, which we call the HITL, or human in the loop. The core principle is simple. For important decisions and actions, a human being should be involved in the final stage. Why is this so important? As the slide lists, it comes down to critical factors like trust, safety, and legal compliance. When an agent is dealing with sensitive data, such as making financial transactions or performing actions with real-world consequences, we need human oversight for accountability. It is also essential for situations involving uncertainty or ethical dilemmas where the agent might lack the context or judgment to make the right call. The human acts as a safety net, or what we call a final checkpoint, to ensure the agent is acting correctly and responsibly. Earlier, we talked about reflect, and reflect is a key characteristic of AI agents. This slide dives into two powerful patterns that enable this capability. We have the react pattern, which stands for reason and act. As the diagram illustrates, it is a cyclical process. The agent starts with the thoughts and what it needs to do. Based on that particular thought, it performs an action, like calling a tool. Then it makes an observation of the result of that action. This observation feedbacks into its next thought, allowing it to adjust its plan based on what happened. This tight loop of thinking, acting, and observing is what allows the agent to navigate complex, multi-step tasks. The second pattern we have here is LLM as a judge. And this is a fascinating concept where you use one LLM to critique the output of another. You can literally ask a model, here is the output from another agent. Is it correct? Does it meet the requirements? How can it be improved? This provides a powerful automated way to check for errors, enforce quality standard, and continuously refine the agent performance. And I'm very sure we all use this. There are some times whereby we ask a particular LLM model to help us with a particular task. When it gives us the output, we now take it back to another model and ask it that, is this correct? So when you are doing this, you are using LLM as a judge. So far, we have primarily discussed the architecture and design of a single agent. But the true frontier is in creating systems where multiple specialized agents can work together. To make this happen, they need a common language, or what we call a standardized way to communicate. Just as protocols like HTTP and TCP or IP enable the internet by allowing different computers to talk to each other, we need protocols for agents. This is what will allow us to build truly complex and scalable multi-agent system. In the next section, we would explore some of the emerging protocols designed to solve this problem. The first protocol we would look at is the multi-context protocol, or what we call MCP. Think of this as a standardized way for an agent to use tools that it doesn't own. As you can see in the diagram, we have a client-server architecture. On the left is our agent, which is the MCP client. It has a simple goal, which is defined by its models and instruction. On the right, we have the MCP server, which acts as a tool provider. It hosts a collection of available tools like functions to interact with a database, send an email, or access a cloud functions. It hosts a collection of available tools like functions to interact with a database, send an email, or access a cloud service. The interaction is pretty much straightforward. The agent can first ask the server to list tools. The server then responds with a manifest of all the tools it has available and how to use them. The agent reasoning model can then look at this list and decide which tool it needs to accomplish its goals. Finally, the agent sends a call to request to the server, asking it to execute a specific tool with the necessary parameters. MCP is really powerful because it decouples the agent from the tool implementation. You can have a central managed server of tools that any agent in your system can discover and use on demand. We've talked about MCP. And if MCP is about an agent using tools, then agent-to-agent protocol, or what we call the A2A protocol, takes this a further step. It is a protocol designed for agents to discover, communicate with, and delegate tasks to other agents. This is fundamental for building the collaborative multi-agent system we have been talking about. Let's look at the flow. We have a workflow agent on the left. It has a high-level task to complete, but it might not have all the necessary skills itself. It then communicates with an A2A server, which acts as a central directory or a broker for community or a broker for a community of specialized agents. The workflow agent can then query the server to get agent cards, which is essentially profiles describing what the other agents, like agent A, agent B, C, and D can do. Once it finds a suitable agent for a subtask, it can send tasks to that agent via a server or via the server. The specialized agent then picks up the tasks from the server. It executes it using its own models and tools and return the results. The A2A protocols allows us to create a society of agents where they can dynamically find and collaborate with each other to solve much larger problems. The core component that makes the A2A protocol work is what we call the agent card. And you can think of this as a business card or a digital manifest for an agent. It is a standardized metadata file, typically in JSON format, that describes everything another agent or system needs to know to interact with it. As you can see in this example, an agent card contains crucial information like the name and provider, which is the basic identification, capabilities, which refers to what special features does it support. For example, can it stream responses or send push notifications? Skills. This is the most important part because it is a detailed list, or it contains a detailed list of the specific tasks the agent can perform, including a description of each skills and the expected input and output. Then finally, it contains the authentication, which refers to how can other systems securely connect to it. The agent card is key to both discovery, which means allowing a workflow agent to find the right agent for the job, and orchestration, which is providing the system with technical details it needs to actually delegate the tasks. Now, once we have multiple agents that can communicate, we can design different models for how they interact. This slide shows two primary patterns, the cooperative and the competitive. On the left, we have a cooperative multi-agent system. In this model, multiple agents work together in a shared workspace to solve a single problem. There is often what we call a coordinator or orchestrator agent that breaks down the problem and assigns subtasks to specialized agents. They collaborate together, share information, and their combined work is then passed to what we call a synthesizer to produce the final solution. You can think of this as a team of specialists working on a project together. On the right, we have what we call the competitive multi-agent system. Here, the same problem is given to several independent agents. Each agent works on its own to come up with a complete solution. This complete solution are then sort of presented to an evaluator model. The job of the evaluator is to act as a judge. You can either select the single best solution or, in a more advanced setup, integrate the best elements from multiple proposals to create a superior final solution. This is pretty much like holding a competition to find the most innovative approach to a problem. All right, we have covered a lot of theory, from the core characteristics of agents to design pattern and communication protocol. Now, let's make this concrete by walking through a practical case study. We are going to look at an application called InstaVibe. This case study will demonstrate how we can bring all these different architectural pieces together to build a sophisticated agent-driven system that solves a real-world user problem. So, what is InstaVibe? At its core, it is an advanced AI-powered social listening and multi-agent system. Its primary goal is to provide hyper-personalized social experiences for its users. It is designed to go beyond simple social networking by using a team of AI agents to proactively understand the user and help them connect with their friends in more meaningful ways. We will now look at specific problems this particular application is trying to solve. So on this slide, what we are showing is the core user problem that InstaVibe is designed to solve. We have a user who is trying to be social. She says, I want to organize a plan for my friends, but I do not know what they like. And at the same time, she does not know what is going on around town. So she has no idea of those two. And this is a very relatable problem, which involves understanding people's preferences or being aware of the current events and then bringing all of that information together to create a successful social gathering. InstaVibe tackles this challenge using a multi-agent system, with each agent having a distinct role. The first one is the social profiling agent. The agent acts like a social listener. It analyzes the posts, events, and relationship of the user's friends to build a user profile for each person, creating a hyper-customized understanding of their interests. Next, the event plan. This agent is responsible for knowing what is going on in the world. It scans the internet for the most updated events and provides. So when it scans the internet for the most updated events, it then provides actual location on the map. Then finally, we have the platform integration agent. This agent closes the loop. Once a plan is formulated based on the insight from the other two agents, which are the social profiling agent and the event planning agent, this particular agent, the platform integration agent, then takes action, automatically creating a post and sending event invite on the platform. So you can see that together, this agent form a collaborative system that takes the user from a vague desire to do something that is concrete and gives up a personalized plan. Now, let's look at what some of the technical architectures that are under the hood for InstaVibe. This is a high-level overview of how the system is built on Google Cloud. On the far left, we have the client, which is the user-facing application. We also have the agent block, which is the core of our system. And you can see that under that, we have several different agent services, like the planner agent and the social agent, all running on serverless containers on Cloud Run. We also have an MCP client and MCP server to handle tool interactions. Then we have the AI block, which shows that our intelligence layer is powered by Vertex AI using the Gemini family of models. For data sources, just under the agent section, we are using Spanner, which is a globally distributed database to host our InstaVibe GraphDB, which is perfect for modeling the complex relationship between users, interests, and events. Then we have the storage block, which allows us to use what we call cloud storage for things like our agent engine buckets. And we have the miscellaneous block, which indicates that we use artifact registry to store our agent container images. Then finally, we have the observability section, which is crucial because we use tools like agent tracing to monitor and debug the behavior of our agents. So in the next few slides, we will zoom in on the specific architectures of the individual agents we discussed. So let's start with our deep dive. Or let's start our deep dive with the most straightforward agent in the system, which is the event planning agent. The event planning agent, its mission is simple, which is to answer the user question, what is going on around town? As you can see from this diagram, this is a relatively basic agent. Its root agent is equipped with one primary tool, Google Search. It uses this tool to find real-time information about local events. However, you can notice how this is constructed. Even the simple agent is built for a multi-agent world. It is structured with an A2A server, which we discussed previously, which is a component that manages its state, memory, and session. It also exposes an agent card, which advertises the skills of this particular agent, the event planning agent, and the skill is finding events to the rest of the system. So this modular design makes it easy for an orchestrator to discover and delegate tasks to it. Then this is a sample code of us creating an event planning agent. And you can see that it's pretty straightforward. Now, we come to the most complex agent in our system, which is the social profiling agent. And this is the agent that delivers on the promise of hyper-personalization. Its job is also simple, which is to analyze a user's social data to build a rich understanding of their interest and relationship. So because this task is not simple, I think I said simple before, right? So we have a single step action that we have designed. And this single step action, it is designed as a workflow agent. So this means it orchestrates an internal multi-step process to arrive at its conclusion. So let's trace the flow within the agent. The first thing that happens is that the root agent kicks off the process. It delegates the core analysis to a specialized profile agent. So in this case, it is a sub-agent, and it examines multiple facets of the user data from our GraphDB from Spanner, looking at their friendship connection, their activity engagement, what they like and comment on, and performing a deeper post-analysis to understand the content they share. It then, from this analysis, so the findings from this analysis are then passed to a summary agent, which creates a concise, structured profile for the user's interest. After that, we have what we call the quality control loop, which has a function called check agent. And what it does is that it evaluates the summary against a check condition For example, it might check if the generated profile is coherent or if more data is needed. So after that, and which is the final the final flow here, is that if the check reveals issues, the root agent can then again modify the output or refine the analysis. So this shows that our agent has the ability to self-critique and improve on its own work. So like other agents, it is built on the A2A framework, and it exposes an agent card also, advertising its own skills, which is advanced social profiling to the rest of the InstaVibe system. Now, let's look at the agent responsible for taking action on the InstaVibe platform, which is the agent we call the platform interaction agent. Its job is to do things like create a new post or a new event invite. To achieve this, we use what we call the model context protocol, MCP, that we discussed earlier. So here, the architecture is split into a client and a server. So the agent itself acts as the platform MCP client agent. When its reasoning model decides that a post needs to be created, it doesn't have the code to do that directly, which we know. So we can see that this flow is simple. The agent MCP client component communicates with the MCP server to get a list of available tools. It then invokes the specific tools it needs. So, and you can see that this is a great example of a decoupled architecture. The agent doesn't need to know the complex internal APIs of the InstaVibe platform. It just needs to know how to speak the standardized language of MCP to request an action. So this makes the system much easier to maintain and scale. And if you are not clear of what MCP means, MCP pretty much means MCP pretty much gives the agent the ability to have access to tools that it does not own. So now we have our final architecture, or our final architectural diagram, which brings everything together. And this is what we call the orchestrator agent. And it acts as the central brain or the conductor of our entire multi-agent system. Its job is also simple, which is to take a high-level user goal and manage the other specialized agent to achieve it. The key to its operation is the agent-to-agent protocol. Let's walk through a physical user request. A user tells InstaVibe, plan a fun weekend activity for my friend. This request goes to what we call the orchestrator agent or the orchestrate agent. The first thing the orchestrator does is to use the A2A protocol to get the cards from all the available agents or all the available sub-agents. This is how it discovers what the event planning agent does, which is to discover. This is how we discover the event planning agent, the social profiling agent, and the platform integration agent. This is what it discovers what they can do. So when it understands the capabilities of all the agents, it then orchestrates an high-level plan. It delegates tasks to the appropriate agent. So to the social profile agent, it sends the task like analyze my friend interest. So once it gets the result, it can now send a new task to the event planning agent, like find local event related to this interest. After the user select an event, it sends the final task to the platform integration agent, create a post and event invite for this plan. And as you can see, the orchestrator doesn't perform this task itself. What it just does is that it intelligently delegates the work to the right specialist for the job. And this is the power of the multi-agent system. It allows us to solve complex, multi-step problems by combining the skills of simple, specialized agents. And we can see, and it is the core of what makes InstaVibe an intelligent agentic application. Now we've done a lot of theory, and I think if you listen to this stage, you should scan this QR code, and it's going to link you to a code lab that you are going to see how you also can create your own edition of the InstaVibe application. Also, if you are listening to this talk from a DevFest, you should scan this QR code to get your DevFest 2025 attendee badge. Bring us to the end of our deep dive into AI agents. We have journeyed from the fundamental concept of what agents are through their core characteristics and the design pattern we used to build them. And finally, we saw how these pieces can be assembled into a sophisticated multi-agent system with our InstaVibe case study. And I hope this has given every one of us a clear picture of why AI agents are truly the new frontier for LLMs, because they represent the shift from models that simply process information to systems that can reason, plan, and take meaningful action in the digital world. Thank you so much for your time and attention, and feel free to connect with me on X or LinkedIn. I'm also excited to see what you all will build with these powerful new capabilities, starting from the code lab I shared before. Thank you.